Let's take a look at this problem taken from the AIME 2019. It says, find the smallest odd prime factor of 2019 to the power of 8 plus 1. Before we move on, don't forget to give a like, subscribe to my channel, and turn on post notifications. This is a very simple problem, but it looks very simple, but we need some slightly more complicated theory to deal with this condition. So when we are looking for odd prime factors of such an expression, I would first let P be an odd prime, and then I would say for 2019 be an odd prime. Maybe I should add that divides this number, and then 2019 to the power 8 plus 1 would then be congruent to 0 mod p. I'm rewriting this as a congruence equation, and then I can do the following operations. By moving the 1 to the other side and squaring both sides, then I would have 2019 to the power 16 is congruent to 1 mod p. Now, speaking of 1 mod p, there are actually some theory to deal with that. Some of you may have already noticed that this is very close to something called Fermat's little theorem, which basically says that for integers that are coprime, a and p, with p be a prime, then a to the p minus 1 is congruent to 1 mod p. Again, this 1 mod p comes out. So we're somehow related. In other words, this theorem is basically saying that when we consider a sequence, say starting from a and then a squared, a cubed, a to the 4, and so on, and I divide every term by p and take its remainder, then after p minus 1 terms, then this sequence will repeat itself, which means this sequence is periodic. Now, however, we may have an earlier occurrence of this kind of a repeating phenomenon, because we have something called order of a mod p, which is exactly describing as the first occurrence of this repeating phenomenon. Say, for example, when p is 7 and a is 2, then the sequence will go like 2, 4, 1, 2, 4, 1. By keep multiplying the previous term by 2, and then we take the remainder again. Then we'll notice that, of course, when after p minus 1 terms, well, in other words, 6 terms, then this sequence repeats itself, because after the 1, then the next term would be again 2, 4, 1, 2, 4, 1, and so on, because 1 multiplied by the number a is just the number a, and then the whole thing starts all over again. But we have actually achieved this way earlier, which is after the 3rd term. So the order of 2 mod 7 in this case is actually 3. But not 6. So on one hand, Fermat's little theorem tells us that this sequence is periodic, but it does not tell us the length of the period. And this order will do this job. However, sometimes the order would really be exactly p minus 1. Say, for example, if p is still 7 while a is 3 instead, then the sequence will go like 3, and then 9 mod 7 is 2, and then 6, and then 18 mod 7 is 4, 12 mod 7 is 5, and then finally we have 1. Then the first occurrence is indeed 6, which is p minus 1 here. So there is a very important property that whenever we consider the order of, say, back to our main problem is 2019 mod p, then we know that because we will always have the repeating phenomenon to occur after p minus 1 terms, and we have this concept of the order, I can say that this order must divide p minus 1, because if this does not happen, then you can imagine that this is actually multiple blocks of one period keep on repeating. And if we do not have that divisibility to occur, then we cannot have these multiple blocks to exactly after p minus 1 terms. So p minus 1 must be a multiple of the order. So in our main problem, we know that because when we bring to the power 16, we have 1 mod p, and so the order in this case, we don't even need to consider p minus 1 yet. We must have d would then divide 16 with a similar argument, but d must not divide 8, because when it brings to the power 8, we still have we're just having minus 1 mod p but not 1. So definitely the order cannot be a factor of 8. But given that this divisor is divide 16, and 16 is just a perfect power, it's a power of 2 to the power 4, then we can say that d must also be a power of 2, and at the same time it cannot be a factor of 8. So the only possibility that remains is that d equals 16. So we know that the order of 2019 mod p is 16. Now given this, now we can bring in the p minus 1, and we can say that 16 divides p minus 1, or in other words, p is congruent to 1 mod 16. So we need to find primes that are congruent to 1 mod 16, and in fact there are not many actually. So starting from the first one, we have 17, and the next one is 33, not a prime, and then it's 49, not a prime, 65, not a prime, 81, not a prime, 97 is a prime, and then 113 is a prime, and so on. So the first number that we're going to test is 17, and next number is 97, and then 113, and so on. So the first one that gets us to 0 mod p wins. So the first one is that when p is 17, then we have to consider this number, mod 17. Then it's actually, when we divide 17, we will have 13 to the power 8 plus 1 mod 17, and then 13 becomes minus 4, so we can need not be minus 1, actually, not minus 4 actually, because 13 squared is 169. So 169 to the power 4 plus 1 mod 17, this is make things much easier. It will become minus 1 to the power 4 plus 1 mod 17, and we quickly realize that it's just 2 mod 17, so it fails. Too bad. And the next number is 97. When we do 97, we will have 79 to the power 8 plus 1 mod 97, and then if we kind of rewrite it, we can rewrite as minus 18 to the power 8 plus 1 mod 97, and it becomes 324 to the power 324 to the power 4 plus 1, which is mod 97 again. And now I can say that 324 to the power 97 is 33 to the 4 plus 1 mod 97, and 1089 to the power 4, not to the power 2, to the power 2 instead, plus 1 mod 97, because 33 squared is 1089, and then I can further divide is 22 to the 22 squared plus 1, and that number is 485 mod 97, and it's actually 0. So yay, we know that 2019 to the power 8 plus 1 is congruent to 0 mod 97, and this is the smallest prime factor, so the answer is 97. So yay, we are done. I hope you enjoyed the video. Feel free to suggest any alternatives in the comments. If you like my videos, make sure to subscribe to my channel right now. Thank you for your support. See you next time.